Alright, in the previous video we have learned how can we delete a node from AVL tree, and we have talked about 4 different cases. Now in this video we will combine all cases together to see the big picture of deleting a node from AVL tree, and based on this logic we will create a delete method in AVL tree. Now we know that when we delete a node from AVL tree there might be cases that rotation is required, so in this case the deletion is same as with the binary search tree. Now in case of rotation is required after deletion, we do rotation to make our AVL tree balanced. So let's say we have an AVL tree like this, and we are going to perform delete operation on this AVL tree over here, and to see that which cases is this, if it is balanced or disbalanced. So for the first thing that I'm going to do, I want to, for example, delete 40 from this AVL tree over here. Now if you look at this AVL tree over here, we can easily see that 40 is located at the left subtree of this AVL tree over here. Now if I delete 40 from here, you can easily see that the parent of 40 becomes disbalanced because the left subtree's height is 2 and the right subtree's height is 0. So this means that this node over here is disbalanced. Now after finding this balanced node, we need to find the condition of this node. So we can easily see that this is left-left condition because the path from 32 to 15 it is left-left. So we have identified that this is left-left condition. Now after identifying the condition, we need to do rotation. So we know that in case of left-left condition, we are doing right rotation. So this means that we are going to do right rotation for this disbalanced node over here, which is 30. Now if we do the right rotation for this disbalanced node over here, it's going to be like this. So the disbalanced node becomes the right child of its left child. Now after doing right rotation, we can easily see that this AVL tree now is balanced. So let's continue to the next case. So in the next case, for example, let's say we want to delete 15 from this AVL tree over here. Now if we want to delete 15 from here, we can easily find out that 15 is less than 70, so it's less than 50, it's less than 20, so 15 is located at the left subtree. So if I delete this 15 from here, then I'm going to check that if the parent of this 15 is balanced or not. So we can easily see that in this case 3 is balanced. So in this case this deletion does not cause any disbalance over here. So this is the case that in which we don't require any rotation over here. Now let's continue to delete another node from this AVL tree over here. Now in this case, I want to delete 65. Now we can easily see that 65 is located at the left subtree because it's less than 70, then it's greater than 50, then it's greater than 60. So we have located it over here. So if we delete this 65 from this AVL tree over here, we can easily identify that in this case, 60, the parent of this deleted node, is balanced. So in this case, our tree is balanced in this case. Now let's continue to the next case. So in the next case, I want to delete 60 from this AVL tree over here. Now if I delete 60 from this AVL tree over here, we can easily identify that the parent of this 60 becomes disbalanced because in this case, 50's left subtree's height is 2 and the right subtree's height is 0. So the difference between them is 2. So this means that 50 over here is disbalanced node. Now after identifying the disbalanced node, we need to identify the condition. Now we can easily see that in this case the condition is left and right because in this case the path from 50 to its grandchild is left and right. So this is left-right condition. So in case of left-right condition, we know that first we are doing left rotation, then we are doing right rotation. So here we are doing left rotation for the left child of this disbalanced node, which is 20. So this means that we are going to do left rotation for 20 over here. Now if I do the left rotation for 20, 20 will become the left child of its right child. Now after doing left rotation, we are going to do right rotation for this balanced node. Now the disbalanced node is 50, so we are going to do right rotation for 50 over here. So this means that 50 will become right child of its left child. So with this, after deletion, our AVL tree will look like this. So our AVL tree in this case is balanced. Now let's continue to the next case. So in the next case, I'm going to delete another node from this AVL tree. In this case, I'm going to delete 80 from here. Now if I delete 80, we can easily see that the parent of 80, which is 90, becomes disbalanced because in this case the right subtree's height is 2 and the left subtree's height is 0. So this means that the difference between them is 2. So here 90 is disbalanced, so we need to find out the condition. So in this case, the path from 90 to its grandchild is right. So this means that this is right condition. Now in case of right condition, we are doing a left rotation for the disbalanced node. So in this case, the disbalanced node is 90. So we are going to do left rotation for 90. Now when we do the left rotation for 90, 90 will become the left child of its right child. So after doing rotation, our AVL tree becomes balanced. Now we are going to continue to the next condition. So the next condition is right-left condition. Now before continuing to the right-left condition, I'm going to insert 105 to this AVL tree. So we know that when we are inserting a node, we are going to compare it with root node. So in this case, we can easily see that 105 is greater than 80. So this means that it's going to be added at the right child. So in the right child, we have 100. So we are going to compare it one more time, 105. So in this case, we see that it's greater than 100. So it's going to continue to the right subtree. So in the right subtree, we have 110. So it's less than 110. So this means that it's going to be added as left child of 110 over here. Now after addition, we are going to continue to delete the other node from here. So in this case, if I delete 90 from this AVL tree over here, we can easily see that the parent of 90, which is 100, becomes disbalanced. So in this case, we can easily see that the 100 is disbalanced because the right child's height is 2 and the left child's height is 0. So this means that this is disbalanced. So after identifying the disbalanced node, we need to identify the condition. So we can easily see that this is right-left condition because the path from 100 to its grandchild is right and left. So in this case, this is right-left condition. So we know that in case of right-left condition, we are doing first right rotation, then the left rotation. But we are doing right rotation for the right child of this node over here. So this means that we are going to do right rotation for 110. So whenever we are doing a right rotation, the node becomes its left child's right child. So after rotation, it's going to be like this. Then we are going to do left rotation for 100 over here. Now after doing the left rotation for 100 will become its right child's left child. So after doing left rotation, our AVL tree is now balanced. Now with this, we have come to the end of this lecture. So in this lecture, we have combined all 4 cases together to see the big picture of deletion of a node from AVL tree. So hopefully everything is clear about deletion of a node from AVL tree. Now based on this logic, in the next lecture, we are going to implement deletion of a node from AVL tree in practice. So see you in the next lecture.